Today we are going to talk about Trial2Vec, a very interesting research paper that is inspired from techniques like Word2Vec. In the same manner, it builds a dense representation of clinical trial metadata that can help us perform various tasks downstream. The key task is finding similar trials using a reference trial metadata. The secondary tasks include query-based trial search and trial outcome prediction. The goal of today's discussion is trying to understand the methodology, the steps within, the key techniques used, and what do they mean and why they were used. Because any paper like this could become outdated fairly quickly, but if you try to understand the target problem, the steps within, and rationale behind those steps, we can potentially apply it to other areas. With that, let's get started. So this is a paper by Zifeng, Wang, and Jimeng. Designing clinical trial is a very critical step as you have to do it. It's a mandatory step if you want to bring any drug to the market. However, it is also a very costly affair, and the sponsors, CROs are always looking for ways to design them efficiently. A part of that is looking at other similar trials to understand what is the standard or draw some inspirations, which is why this problem becomes critically important. If we can find a trial which or set of trials similar to what we are trying to do, then it does help us significantly. So they have done two things. They have tried to use the meta structure of trials, which basically means they have not used the data collected through the trial. They have not used the patient level data, but they have used the metadata of the trial, which is available on websites like clinicaltrials.gov. That includes title of the trial, description, eligibility criteria, outcome, disease, intervention, maybe phase, target enrollment, and so on. The other key component here is they have tried to use UMLS, and we'll look into that shortly. They have three critical applications for this proposed system. Finding a useful set of trials when you provide a reference trial. Second is finding useful set of trials when you provide a query, which can be based on certain fields within the metadata. And third, trying to predict trial success or failure rate using metadata. All right. So this is the introduction, which basically talks about some of the prior work, self-supervised learning, how the sentence embeddings were used. Embeddings is basically numerical representation of text. It can be generated at word level, it can be generated at sentence level, a document level, and so on. As machines understand only numbers, there is this critical step of converting the text into numerical format. Earlier, it was done using sparse embedding techniques like term frequency inverse document frequency or BM25. But since I believe Trial2Vec was invented, dense representations are very popular and they have increased the efficiency of the application significantly. Since these documents are very lengthy, sentence embeddings might not be a good idea, which is why they are trying to convert entire trial into embeddings. And then they have used this technique called as contrastive learning, which is aligned with self-supervised approach. What contrastive learning tries to do is, for a given example, let's say we have an image of otter. It will create a positive sample and a negative sample. A positive sample can be created by altering the original data in a minor way. You can tilt the image, you can flip it, crop it, or you can find another label data. Here they have no label data, so they'll use some sort of operation to create the positive sample, and then there has to be some technique which creates a negative sample, and then contrastive learning we'll try to learn the representation and similarity and dissimilarity between the two. All right, so this approach is basically looking the meta structure, which is the metadata, which you can see in this table here. If you go and look at clinicaltrials.gov, you can look at a bunch of metadata which shows you the official title of the study, the intervention, the drugs which are being used, the locations, the study plan, number of arms, the dose used in each arm, and so on. So as I said, this is the data which is used to describe a trial, but this is not the data which is being collected from the patients in a given trial. They talk about some of the previous work which was done using dense retrieval methods, but it was not enough. It wasn't done at this large scale. Now let's think about why using just a query as an input might not be enough. There are two approaches through which we can search for relevant trials. One is we can provide a query. We are looking for indication X or intervention Y, phase 2, and so on. Then we can try to fetch the trial. And the other approach is we give metadata for trial and then try to fetch a trial. Analogy would be we're trying to search a car, so we can give all the details, what sort of horsepower we need, how many seats, some other functionality, and search for the list of cars which match our requirements. The other approach is basically give a car which already exists in the market and then let the system find similar cars. They are following the second approach here. So this image is a good overview of what they're trying to do. A lot of information here, but let's start with the top left corner. Two types of inputs are being provided. One is this trial level metadata. Each trial can have title, disease, intervention, and other associated metadata fields. And the second piece of input is external knowledge base, which is this UMLS, Unified Medical Language System. It's a set of comprehensive tools and resources developed by National Library of Medicine. For this use case, think of this as dictionary of dictionaries. So it will have multiple dictionaries within it, like SNOMED, ICD, LOINC, CPT, and so on. Example of why this might be useful is seen here. So in ICD-9, one event or one term can be represented as atrial fibrillation. The same term in NCI thesaurus can be represented as AF. The same term again can be represented in MEDRA as AFib, and in other dictionaries it might be represented with even more variations, which is why we need this dictionary of dictionaries to have some sort of unified medical language. All right, so these are the two input pieces. The top right corner talks about methodology, what we are trying to do. The methodology is essentially at two levels, at local level and at global level. So we try to learn the representation through embeddings at local level, and then we try to learn the representation at global level, which is at the top part here. For each of these two levels, whatever input is provided, we try to create a positive sample and a negative sample, as we saw in the contrastive learning. So for trial 1, this is the global level, we create a positive example, we create a negative example, and this Trial2Vec encoder can use a loss function like InfoNC and try to execute contrastive learning. And at local level, we can use UMLS to understand or extract useful entities, medical entities. And then for each of those entities, we can try to create a positive sample and negative sample, and then that can be further used to do contrastive learning at local level. Bottom left part, this is a zoomed in version of how local level learning happens. For a given trial, let's say trial number 4, we have these individual meta fields. title of the trial, intervention, disease, and we also have some contextual information. Each of these fields are individually converted into embeddings using trial-BERT. These embeddings are local embeddings, which are represented in yellow and green here. And then these individual embeddings can be combined to create global embedding, which is represented in gray here. And then the final part of the diagram is how these are applied for the three specific tasks. So using these global embeddings, we can do trial to trial search. So user provides a reference trial, we create that trial information, metadata into global embeddings and do some sort of similarity matching to find relevant trials. The second application is query trial search, where user can provide some partial information to form a query, which is not the entire trial, but maybe just the title of the trial, along with intervention and or disease or some other fields. And then that can be used to create local embeddings, and then we can do similarity search at local embeddings, maybe combination of local and global embeddings to find similar trials. And finally, there is the third task of trial termination prediction. So I don't think that was the real intent of this paper, but since they had already created trial level representation in the form of embeddings, this is an attempt to see if those embeddings can capture some information in terms of whether the trial is going to succeed or fail. All right, so let's zoom into the methodology. There are two levels of embeddings: global embedding, which is for the entire trial, and local embeddings, which are for given fields which are created. However, not all local fields are equally important. Some fields like title of the trial or intervention might be far more valuable than some other fields like location of the trial. So point number one, we have to find a way to capture that information somehow. And this is where they are talking about aggregating the local embeddings in a clever way. So we don't like average out, consider each embedding or each attribute as equally important. This is why they're using learnable attention module. What this learnable attention module is doing is allow model to focus on specific parts of the input while producing the output. So not all parts are considered as equally important. Then each section within the methodology zooms in on individual steps. Step one is we have to somehow convert the textual information into numerical representation, and that is done using some sort of encoder. So BERT is a common encoder model. They can use BERT as is. However, BERT is trained on a general text. So the corpus which is used would have all the information from other domains, say finance or astrophysics and so on, which is not really relevant. Those terminologies are not really used as part of what we're trying to look at here. So they used a variation of BERT called BioBERT, which basically means the same architecture was used, but there was a continuous training of the weights. And for our task, the weights from BioBERT are more relevant. So they start with the weights from BioBERT, but also continue the training. And the reason why they do that is, and this is my guess, whatever corpus BioBERT use might not have some information which clinical trials corpus would have. Some entities, some maybe drugs, some conditions. This is another step which is trying to align the weights further using this masked language model loss. This is a common loss. What it is doing is, in a given text input, it will try to mask or hide certain words and then see if the model can predict those masked words. And we can apply some sort of binary cross entropy loss, since the outcome would be binary. Either you can guess the word or you won't be able to guess the word. So in order to do that, they use the data from clinicaltrials.gov, medical encyclopedia, and Wikipedia. I'm not sure why they use Wikipedia articles. So either they use Wikipedia articles from clinical trial related pages, or I'm guessing they used this as a balancing mechanism so the model doesn't over adjust the weights for the biological corpus and forgets some information which it learned from general words. Then the second section of methodology, they're talking about creating global and local embeddings. So we spoke about why we need two levels of embeddings, and this is where the need of hierarchical embeddings come into the picture. Hierarchical embeddings are essentially used for hierarchical structures, so you can create embeddings for each word and then average it out in some way to create embeddings for a paragraph or entire document and so on. So there are various averaging methods, various methods which can help us roll up that information. um, Average pooling is one method which is commonly used for the previous methodologies they have referenced, but it is not very effective because it treats all the individual components equally, and we just saw some key components, some key pieces would have more information. So they have used multi-head attention, and multi-head attention is a extension of self-attention where attention mechanism is applied multiple times in parallel using different projections of the input. One simple example would be the cat chased the mouse. So one head might focus on the subject object relationship that is between cat and mouse, while the other head might focus on the word grammar or order, and the third head might focus on some other aspects and so on. So it basically tries to capture more information. Think of that as having multidimensional convolution layers. We are using this sort as a good mechanism to capture the imbalanced information present in the local embeddings. The next section, which is 3.3, talks about how we want to create these samples, negative and positive samples, at global level and local level, so it can be used as part of contrastive learning. So this is a given data point, a given trial. It will have these components like title, intervention, disease, outcome, and so on. In order to create negative sample, the title is replaced. So we have a different title, all same attributes. Title is a key component, so this becomes a dissimilar trial or a negative example. Although I'm not really convinced this is the best way to create a negative sample, but again, I guess they're trying to do this without labeling, so maybe some sort of balancing act here. And then they create positive example just by dropping one of the attributes. And now we have the original data point, negative sample, positive sample. Remember the example of otter we looked at? And info NC is a common loss function which is applied. What we're trying to do here is denominator in numerator. We are looking at global embedding of the ith example, where I is pointing to a particular trial in a set of B trials. So we have global embedding of given example, global embedding of positive sample pair, and in the denominator we have global embedding of the given example and negative samples global embedding. And then these pairs are basically passed in some sort of similarity function, and then we take exponent and then log, and this is the global loss representation. Similarly, we try to do this for local level embeddings or local level contrastive learning, where we have set of attributes. This is where the UMLS comes into the picture. to create positive and negative examples, because UML understands what is similar and what is different based on the hierarchy we have in those dictionaries. One question I had is, they point a very interesting observation here. Unlike general text, two medical texts can be overlapped word-wise dramatically, but still describe two distinct things. And this is an example they provide. A phase 1 open label 2-part multi-center study to assess safety and efficacy of olaparib. If you replace this drug with something else like vitamin D, it's a completely different trial. So the word overlap means very little in this context, which is a good point. But shouldn't multi-head attention take care of this? And that's what my understanding was. If you know why this would not take care of examples like this, feel free to comment below. Now they have a way to create positive negative example at local level, then they calculate local loss, and then the total loss is calculated by global loss plus local loss. All right, so that was the methodology. Now let's look at application. There are 3 applications for trial level similarity search. They look at global embeddings. Then we have query level search. This is where the local embeddings and global embeddings are utilized. And then we have trial level prediction, which is success of trial, which is where they use global embeddings and then add a layer on top of that, a fully connected layer, so that it can translate those embeddings into something a bit more binary. All right, so then they have designed few experiments to understand how well the model is performing, if the representations have any meaning by itself, and we'll look at the results quickly. They also talk about the data setup, how they created the validation data. So they sampled 160 trials, then use some sparse technique to find 10 related trials each. That gives them 1600 labeled trials. And then there were 4 domain experts which looked at these pairs and ranked them as 0 or 1. 0 meaning the pair represents similar trials, 1 is not a similar trial. And they go into the methodology, how they define 0 and 1. The 3 metrics they looked at here is precision at K, recall at K, and then DCG. And I was not very familiar with the third, but it essentially represents the quality of the rankings we have, normalized, discounted, cumulative gain. Yeah, so these are the results. If you look at precision at 1 to 5, recall at 1 to 5, and DCG at 5, each row represents a method. Some of them are sparse methods, and then we have dense methods, and Trial2Vec outperformed all the methods listed here. So they also try to plot some graphs for all the 5 or 6 specific experiments they had designed. And if you look at this graph, you can see title is a very critical component. It wasn't precision at 1. If you find 5 results, then 4 of them are relevant. And then recall is showing you the information we were able to collect. How much did we really leave behind? It was not part of top 2 or top 1. All right, so this is an interesting analysis where they try to project those embeddings, which are, I believe, 768 dimension. So any embedding model would convert the given text input into fixed length vector. That fixed length is dimension of the embedding, and in this case the model was creating embeddings with dimension at 768. Intuitive way to think about this is any data point is now being represented, be it a trial or a title of the trial, in a 768 dimensional space. So we can't really visualize that space. as a result, we try to project it into two-dimensional space using techniques like Disney, and that's what they have done. And interestingly, it creates these clusters which are heavily influenced by indications or disease, which is one of the attributes of trial metadata. These results show the output of the third task, which was trying to understand the success or failure rate. As you can see here, Trial2Vec outperform the previous methods. We looked at AURC, and also precision recall AUC. Yeah, so that's basically it.